Hi, welcome back to another episode of Algebra in Words, the video series on YouTube. In this video, we're continuing our discussion on radicals, and in the last video we looked at simplifying radicals, but in this video we're going to look at combining radicals, such as addition and subtraction of radicals. So let's get started. I have a couple examples on the board, and we're going to go through these progressively. So the first thing that I want to say is in order to be able to add or subtract radicals, they must be like radicals. And you add or subtract radicals much in the same way that you would like terms, and I'm going to show a comparison of that. But first I want to say, what is a like radical? It means that the radicals must have the same radicand and have to have the same root. So anyway, we'll evaluate that criteria as we look at these examples. So our first example is this: 8 square root of 7 plus 2 square root of 7. And the question is, are these like radicals? Now, to make a comparison and to bridge you from something that you already know, which is like terms, above I have 8x plus 2x. And these are like terms because the variable is the same and the exponent is the same. They're both x to the power of 1. So the variables are like variables and they're like terms. Therefore, we're able to combine them by adding or applying the operation of the coefficients. 8 plus 2 is 10, so 8x plus 2x is 10x. And like radicals, and the concept of adding and subtracting like radicals is basically the same, except you're dealing with radicals instead of just plain terms. So the question is, are these like radicals? And the answer is yes, because it fits the two criteria. The radicals are the same, meaning they have the same radicand, they're square root of 7, but also they have the same root. They're both root 2, or we call them square roots. So since they're like radicals, we can combine them by combining their coefficients. 8 plus 2, just like the example above, is 10. And we leave the like radical attached. 10 square root of 7. Let's apply that criteria to the next example. And the question is, are these like radicals and can we combine them? We have the square root of 6 plus the square root of 17. And in short, these are not alike. The roots are the same, but the radicands are different because one is 6 and one is 17. So they're not alike and they cannot be combined, and it's as simplified as it can be. So basically, it's not like we say no solution, but it's simplified already and we can go no further. We cannot combine these. So I'm going to circle this just to show that it's already as simplified as possible. Let's look at the third one. The square root of 6 and the fourth root of 6. Are these like radicals? And you might notice they both have the common radicand of 6, but they do not have the same root. One is the square root, one is the fourth root. Therefore, these also are not like radicals. They cannot be any further combined, and they're already as simplified as possible, so we're going to leave that as is. So I'm going to pause the video and put a few more up. I have 3 more examples on the board. The first one is just another exercise of identifying like radicals and combining like radicals. We have 9 square root of 5 plus square root of 2 minus square root of 5. So are any of these like radicals? And hopefully you identify this term and this term as like radicals because they have the same square root of 5. So we can combine them by 9 minus the unwritten coefficient 1 is going to give us 8 square root of 5. And the square root of 2, there's no like radical with that. So we're just going to rewrite that as plus square root of 2. And that's done. Is there any proper order that these need to go in? No, I think that's pretty much good enough. Let's look at the next one. Now, this one is an important example because, now first of all, in their current form, these are not like radicals. But also, they're not simplified radicals either. So the goal from here on out is to simplify radicals as much as possible. That's why we went over simplifying radicals in a previous video, because now's a time when that's going to come into play. So remember that to simplify a radical, you want to factor it into any perfect, in this case, perfect square factors and any remaining factors and split them up. So when looking at 9 square root of 18, focus on the 18. What are any perfect square factors of 18? Hopefully you think of as 9, that's the perfect square factor, and the remaining factor is 2. So we're going to break that up as 9, the square root of 9 times 2. And if you really wanted, you could break these up into their own individual square root factors, but I don't really see a need to do that as long as you understand that you can do it. Minus, rewriting that 2, and we're going to do the same to the square root of 8. Can we split up the 8 into any perfect square factors? Yes. Perfect square factor of 4, and then its remaining factor 2, like this. And now that we did that, now we're going to extract out any of the perfect powers. So for example, let's go down a level, and we're going to rewrite the coefficient 9. And now, since this is the square root of 9, let's take the square root of 9 out as 3. And write the remaining root 2. And now same thing for this one. Bring down the coefficient -2. And now we're going to take the square root of perfect power 4. The square root of 4 is 2, so that comes out as this 2. And then again, the remaining factor of 2 is not a perfect square, so we're going to leave that under the radical as square root of 2, like this. Now the next step is, let's combine by multiplying any factors out in the coefficient area as we can. So 9 times 3 is 27, and 2 times 2 is 4, and I'm just keeping the sign negative with that. So now let's look at what we have, and I'm just going to bring down the radicals with them. So 27 square root of 2, and -4 square root of 2. And if you notice, now do we have any like radicals? Yes. This square root of 2 and this square root of 2. And now you can probably see the significance of why we simplify radicals down as much as possible, because it may reveal, once simplified, that they are like radicals that can be combined. And the goal is to simplify and combine as much as possible. Now we can add or subtract. 27 minus 4 is going to give us 23, and square root of 2. So that problem is done. And now let's look at the last one. 3 square root of x cubed minus square root of x. So when evaluating these, are these like radicals? No, because one of them has x cubed in the radicand and one of them has x in the radicand. But the question is, can these be simplified down anymore? So let's try to figure that out. Now this is x cubed, but this is the root 2. So could we simplify that down anymore if we break up the x cubed into any perfect square factors and what remains? And the answer is yes. If we recall the product rule, or use the reverse product rule, meaning to split up the x cubed into x squared times x to the 1, or just x, under the radical, now it can be broken up and we can take the square root of x squared out. So it's going to be 3x. This x came from the square root of x squared here. And the remaining radical is square root of x. And then this is, we're just bringing down this minus square root of x. But now we have an interesting situation because now we do have like fractions, like radicals, but can we do anything with them? Now what we're supposed to do is subtract the coefficients. So since this is 3x and this is basically -1, let's just write that out as if we were to do that. So, and let's do that up here. So 3x minus 1, and I'm going to put that in parentheses because we're multiplying that by the remaining square root of x. And this is the answer. This is the final outcome. So just to summarize what we did in this one, we broke up the x cubed into any perfect square factors by using the reverse product rule of exponents of bases. So we split this x cubed into x squared times x to the 1. And we did that so that because x squared is a perfect square, and we took the square root of x squared, which came out as x. That also left this x as the square root of x, which also is a like radical with this square root of x. And then, because they're alike, we add or subtract their coefficients. So we did 3x minus the unwritten 1, that's here, and we had to put that in parentheses so that we could write what remains, which is the common factor of x. And basically, that's how you have to do that. So that concludes this video on adding and subtracting radicals. It basically covers and summarizes everything you need to know. Remember that if you have like radicals, which means the root is the same and the radicand is the same, they're alike. And when they're alike, you can combine them by adding or subtracting by their coefficients. If they don't start alike, which they may not, that's why you want to simplify them down as much as possible, because it may reveal that you do have like radicals, and then you combine them appropriately. And if you need to break apart any factors under the radicand, whether it be the numbers or whether it be variables raised to a power, use the appropriate power rules to split them up appropriately so that you can extract any perfect power factors. Then that may reveal that there are like radicals, and then you combine appropriately. So again, that concludes this video on this. The next step is going to be multiplying radicals, and we're going to cover that in the next video.